Have heard, the fire alarm has been cleared. We are all okay. Nothing is on fire. Everything is fine. Thank you. Thank you. Next piece of administrivia, if you have any device that is capable of making noise, please convince it not to, because if it does, everyone will stare at it and you and mock both of you on Twitter. Our next talk is by Tony Ojeda. He is going to be speaking about human-machine collaboration for improved analytical processes. Please make him feel welcome.
Thank you very much. Hello, everyone. My name is Tony Ojeda, and I'd like to welcome you to my talk on human-machine collaboration for improved analytical processes. So before I dive into the meat of the talk, I'd like to tell you a little bit about me and my background, and then we'll go ahead and jump right into it. So I'm a data scientist at Follett. They are a higher education, wholesale, and retail company, and I use Python, analytics, and machine learning to build data-driven processes that help drive that company's business there. I'm also the founder of District Data Labs, which is a data science research institute and open source collaborative based out of Washington, D.C. We have a variety of open source projects that we build with Python, and we use Python extensively in our corporate training and consulting offerings as well. I've co-authored a couple of books. There's Applied Text Analysis with Python, which is an O'Reilly book that's coming out this fall, and then the Practical Data Science Cookbook, which was published by PACT a couple of years ago. And this is my fourth time speaking at a conference. Last year I spoke at Data Day in Seattle and at PyData Carolinas and PyData DC. I originally got into data science and analytics from a business background. So I studied business in school and started off working as an analyst. And it really wasn't too long before I figured out that if I learned a little bit of programming, I could get my work done a lot faster, and I could do a lot more than the other analysts that I was working with. And so I taught myself how to program, first in VBA, creating these little baby self-contained applications in Excel and Access. And then from there, I taught myself how to program in R. And then about 4 years ago or so, I started programming in Python, and I have to say, I fell in love with it almost immediately. And this was right around the time that pandas was starting to get popular, and so I was like, oh yeah, this is going to make my transition from R to Python so much easier. And so I made that transition, continued analyzing data with Python now, and then I started to get into some of the machine learning stuff, and this was right around the time that scikit-learn started adding a bunch of new features that made doing machine learning a lot easier. And so not only was I learning about all these different cool algorithms that I could use, but I was able to easily implement them, swap one out for the other in my pipelines, and compare all their results. And at that point, I was like, this is awesome, I'm Superman, right? I could do all these things, and I thought it was like super awesome. And so now it's been a few more years, and the advances in machine learning and automation are starting to come together, and we're starting to see a resurgence of artificial intelligence. So things that were harder to automate previously are starting to become a lot easier now. And in fact, if you read any technology publications in the last few months, chances are you've come across headlines like these, right? So artificial intelligence and the end of humanity, artificial intelligence is going to take your job, right? All very scary kind of dystopian things. And so naturally, I started to ask myself, well, could what I do actually be completely automated? And so, of course, I did some additional research on this to basically see if I could find some information that would tell me and help me figure out how long I had before I was essentially obsolete. But as I was reading through all these papers and articles and blog posts, I started to come to the realization that maybe I was focusing on the wrong question, or if not the wrong question, not the most applicable one to me in the near future. And so instead, I decided that a better question would be, how can we combine human and machine abilities to produce better outcomes than either could on their own, right? how can we leverage the power of technology and combine it with the unique abilities of humans to accomplish things that we couldn't achieve from a purely human solution or a purely automated one? And I think this leads to a very important perspective, and that perspective is, instead of thinking about a human versus a machine, thinking instead about humans plus machines working together toward the same goal. And for me, this is much more exciting and I think worthwhile as an area to focus on. I truly believe that we've only scratched the surface of the things that humans and computers can do together, and that's currently being overlooked, I think, in favor of these scary dystopian headlines. And we should be seeing more headlines about this, and I'm hoping that this presentation is my first contribution to that. All right, so we've talked about humans and machines collaborating and the importance of it, but how exactly do you go about designing these collaborative analytical processes? Well, to answer that question, we first need to know what is an analytical process. So when I'm talking about an analytical process, I'm talking about a series of tasks for ingesting, transforming, analyzing, modeling, or visualizing data. I put an image up here of the data science pipeline, which is a general process that most analytical projects follow. The pipeline itself is an analytical process composed of other analytical processes which themselves have tasks that have to be completed. And so I think from that, you're starting to see that in order to design an analytical process, or just about anything, you need to start with deconstructing what needs to be done. And so we need to deconstruct the process into tasks, and those tasks into steps that are small enough where we can determine which should be performed by a human, which should be performed by a machine, and then how to weave the steps performed by each together so that we end up with a process that runs as smoothly as possible. And in order to do that, we need to ask ourselves a couple of important questions. So what types of tasks are humans better at, and what types of tasks are machines better at? And the idea here is that we'll probably want to assign tasks to whichever is going to perform it best or the most efficiently. So let's take a look at the types of tasks humans are good at and the types of tasks that machines tend to be good at. So for humans, the first type of task I have up here is a sensory task, right? Things that require the senses. So a good example of this is visual pattern recognition. The human visual cortex has been trained over millions of years now to be able to process visual information and recognize patterns. And as a result, we can look at something and almost immediately process what it looks like and make a decision about it. Nowadays, machines are starting to get a little bit better at this, but they're not quite there yet, at least not in the examples I've seen. Next, we have tasks that involve kind of a social interaction or language or collaborative communication. Humans are very good at this, whereas machines still have a long way to go. We're also good at tasks that require either domain or general knowledge, and that gives us context, right? Machines don't typically possess the amount of context that's necessary to handle these types of tasks. They only know what they know. And then we have tasks where flexibility, adaptability, and creativity are important. Circumstances tend to change a lot and often, and humans are relatively good at adapting to change. And finally, we have these more exploratory or investigative tasks where we don't know exactly what we're looking for, but we'll know when we find it. Humans are much better at that, whereas machines usually need some kind of a goal or a direction that you point them in so that they're able to optimize towards that. All right, so now that we've done humans, let's do the machines. So for the machines, first, there's tasks where precision is important. These machines are very precise calculators, whereas humans typically estimate, right? Close enough is usually good enough for us. Machines are also good at processing vast amounts of data extremely quickly, whereas humans are prone to information overload if too much information comes at them too quickly. And then the next one has to do with information storage and recall. Machines can store large amounts of information and recall things very quickly and precisely, whereas humans are relatively forgetful, right? We're constantly forgetting names, birthdays, car keys, all that kind of stuff. And then finally, we have repetitive tasks that need to be performed exactly the same way every single time. Again, machines are good at this, whereas humans are often inconsistent, both across iterations of tasks performed by the same human and also identically repeatable tasks that go from one person to the next, right? Okay, so in order to design a collaborative analytical process, we need to deconstruct the process, right? We need to determine which steps should be performed by the human and which should be performed by the machine. And finally, we need to identify the points of interaction where one takes over for the other or where information is exchanged and ensure that those are intuitive. And these points of interaction are called the interface. And the interface is actually really important because it's where your process is most likely to break down at that area of handoff. When you spend time trying to design processes where humans and machines are working together, you end up actually spending a lot of your time trying to design these interaction points. And they can run the gamut of simplicity to complexity, from passing a value to a variable to capturing complex information via a web application. All right, so now that we know a thing or two about designing analytical processes, let's take a look at how to apply that to collaboratively performing exploratory analysis on a data set. So this is a framework I put together for data exploration. I created this framework last year and spoke about it at the conferences I mentioned previously. I also have a poster on this framework that I'm going to be presenting during the posters tomorrow. So if you're interested in this, make sure to stop by there. So we're going to go through the framework, and for each of the tasks within the framework, we're going to look at what type of work is required to do that task, and then determine whether it should be automated, whether it should be done manually, or whether there's an opportunity to blend the two. So going back to this framework here, the framework has two phases. There's a prep phase and an explore phase. And the first two stages of the prep phase, identify and review, are meant to prepare the human for exploring their data. So you're not really doing any coding there yet. In the identify stage, you're basically going to look at your data and try to identify the different types of information that are contained within it, as well as the real-world entities that are represented in the data. In the review stage, you're basically going to review the different transformation and visualization methods and tools that are available to you for exploring your data. And then that brings us to the third stage of the prep phase, the create stage, where the goal is to prepare the data itself to be explored. And the way that we do that is by creating additional categories and categorical fields that are going to provide us with different perspectives on our data. And that's where the programming actually begins. So that's where we're going to start drilling down a little bit and deconstructing things. So what happens when we try to incorporate some level of automation into the steps in the framework from this point? Well, the first task that we encounter is category aggregations, where the goal is to create higher level categorical variables out of the categorical variables that we currently have in the data. So we're essentially identifying categorical variables that have a lot of unique values, like more than 10, for example, and trying to find ways to distill those down to fewer categories so that we can take a look at it more intuitively. And so here's an example. This is from a vehicle data set. It has a transmission column that has like 45 different unique values in it, but they can all be distilled down into either an automatic transmission type or a manual one. And so let's take a look at what's required to do that, right? What's required to do these category aggregations. So first, you need to identify the actual categorical fields and their unique values that are in your data set. And then comes a bunch of stuff that like humans tend to be good at, right? Like taking a look at the categories and understanding what the words mean, using your general or domain knowledge to know which ones to group together into other categories, and sometimes creativity depending on how the categories are laid out. So automation of this particular step would probably be pretty difficult. It would require a lot of like natural language parsing, lexical database lookups and interpretation, calculating semantic similarity, and then regenerating text for the new categories. And that's all really computationally intensive and time-consuming. Meanwhile, you and I just took a look at the categories on the previous slide, and we almost immediately were able to figure out that we could group the categories into automatic or manual. So this task is probably most efficiently done by a human, but that doesn't mean that a machine can't contribute to making things easier for us, right? So, for example, it could help identify the fields in the data that could potentially make good category aggregation candidates, especially in data sets that have a lot of columns, right? So maybe it automatically finds categorical fields with 10 or more unique values and then presents them as potential candidates for category aggregation to us. And this way, the human doesn't have to comb through the entire data set looking for columns that match this criteria. All right, so the next task in the create stage is continuous bidding, and as the name implies, it involves creating new categories by bidding continuous variables based on how high or low their values are. So let's take a look at what steps are required to do that. So the first thing that you'd have to do is identify the continuous variables in your data. You'd have to do some comparing, ordering, and then segregation of them into different buckets. You'd have to have some knowledge about whether higher or lower values are better or worse. And then after you're done with that, you'd have to meaningfully name the different categories that result. And so automation of this, taking a look at these steps, right, would be relatively easy as long as you had a predefined number of bins, so quartiles or quintiles or deciles or percentiles, and intuitive category labels to go along with them. So the machine can do most of the heavy lifting here, while the human just has to ensure based on their domain knowledge that the resulting categories were able to be interpreted correctly. And in fact, like, you can do this in just a few lines of code, right? And once you've basically identified the numeric columns, you just need a for loop and then a line or two of code for each level that you're binning at, and then the pandas QCut method can take care of the rest from there. And so here I've put up an example for quintiles, deciles, and percentiles. The third step in the create stage consists of clustering your data in order to group records with others that are similar. So just like binning, this can be done at different levels, usually defined by the number of clusters. Now, unlike binning, you won't know in advance here what each cluster means, the number of levels you're going to end up with, or the number of clusters that are going to end up being in each level. So let's take a look at what the requirements are for clustering. So first, you need to identify the numerical variables in your data. You need to cluster the similar records together, and then determine the quality and appropriate numbers of clusters, and then finally come up with a meaningful name for each of the resulting categories. Taking a look at these steps, it looks like automation of the first three would be relatively straightforward. The fourth would probably require some context, some domain knowledge, and also some natural language generation to automate, so that's much more kind of computationally intensive. So perhaps we could have the machine perform the first three steps here, and then design an intuitive way for it to present or communicate the cluster attributes to the human afterwards so that they can come up with the appropriate labels for each of the categories. And that brings us to the end of the prep phase. So now that our data is prepped, we're going to move on to the explore phase, and the first thing we're going to look at in this phase is the filter and aggregate stage. The overarching goal of the explore phase is to gain as many useful perspectives as possible, which can then turn into as many insights as possible. And by filtering, you're essentially making the data smaller based on some condition or conditions, so that you're looking at either less rows, less columns, or both. And by aggregating, you're grouping all the different categories that now exist in your data as a result of the work you did in the prep phase, performing calculations and comparing the different groups to each other. Some common visuals that you'll see in this stage include things like bar charts and heat maps, which I have up on the slide, one of each there. And that's because they tend to capture this type of information extremely well. So let's take a quick look at what's required to do the filtering and aggregating, and then determine how best we can split up that workload. So first, you'd have to identify both the categorical and the numerical variables. And then you'd have to do some filtering or some subsetting of the data set by categories. You would aggregate up based on those categories and calculate different values for the numerical fields, like the sum and the mean, all that kind of stuff. And then at the end, you would interpret those results and determine what's useful. Now, I would argue that a machine could probably do the first of these much more efficiently than a human, and that a human could do the last one better than a machine. But there's actually a challenge here, right? The machine's perfectly capable of performing all the filter and aggregate combinations, but for most data sets, that's going to be a lot, right? So there needs to be an intuitive way to filter down those results based on some criteria, so that when the results are handed back to the human doesn't have to look through hundreds or thousands of perspectives. And you can put that criteria at the beginning of your process if you want to, but if you put it at the end instead, you'll sometimes find that the machine may actually end up aggregating data in useful ways that you as a human may not have thought of. So there's kind of a balancing act there between efficiency and insight that needs to be taken into consideration. Now, in terms of interface for this, some of the best examples I've seen have involved both having a visualization like a chart or a graph, and also a templated natural language explanation of what the graphs are showing, right? And as long as you have your go-to visualizations ready, which you should have done during the prep phase of this framework, and you have a good template for the explanations, the little bit of extra work that's required here tends to produce some really valuable results. Okay, so the next stage in the framework involves analyzing relationships between different fields or columns in the data. And this is typically done by looking at scatter matrices and scatter plots, and calculating things like covariance, correlations, and other metrics that help to describe the types, directions, and strength of relationships between the fields in your data. So let's take a look at what's required to do this. So first, you have to start off by identifying the numeric fields in your data and comparing the cross distribution of values across all combinations of those numeric fields. That's going to let you be able to identify the existence, direction, strength, and type of relationships, and then from there you just need to determine which relationships or lack thereof are interesting or insightful. And so just like for filtering and aggregating, the machine could perform the first three steps here pretty efficiently, and not just for the data at its most granular level, but aggregated higher levels as well. So again, there needs to be some kind of criteria for determining which relationships we want to keep and which ones we don't, and also the same considerations we reviewed are going to apply here as well. As far as the interface for this, the combination of visualizations like scatter plots and natural language description works very well for these types of exploration and analysis as well. In addition to field relationships, we're also going to want to explore entity relationships in our data. And whereas field relationships were relationships between the columns, entity relationships are going to be relationships between the rows, or better yet, between the real-world entities that the rows represent. These relationships between the entities, some are going to be stronger and some are going to be weaker, and the way that we analyze these types of relationships is through graph analysis. So let's take a look at what that requires. So the first step here is identifying the hierarchical entity levels that are in your data. From there, you also need to identify the similarities between entities and the strengths of those. And then once you have that, you can start to identify clusters, communities, and sub-networks that are in the larger network itself. And then finally interpreting those relationships and what they mean in the real world. And so by combining Python tools like Pandas and NetworkX and GraphTool, most of these steps can be automated. And just like in the other stages, the challenge comes with the exchange of information between the human and the machine. The human has the domain expertise to interpret the results of the graph and determine what's useful, while the machine has the raw computational power to generate these graphs and then traverse them looking for patterns. The resulting interface for this type of analysis is often going to involve a network graph like we saw on the previous slide. And those can sometimes be difficult to look at, especially when there's a lot of nodes or edges in the graph itself. So when you're considering the interface here, you may want to consider drilling down into like the subgraphs or the ego graphs or the specific communities and visualize those, as well as having some kind of a natural language description of those relationships. So, all right, so we've made it through the main stages of the data exploration framework. So let's review what we've done and take a look at some key takeaways here before we wrap up. So first, I hope that I've conveyed that the design of human-machine collaboration into these analytical processes is something that's not only possible, but important and very useful. As we saw, the way to design one of these processes is by deconstructing it into the different tasks that are required, breaking those tasks down into the different steps, and then evaluating those steps to determine what contributions the human versus the machine should make and how they should work together. While we're at it, we want to pay special attention to the points of interaction, the interface that we were talking about, and how we can design those to be as intuitive as possible. And finally, I'd like to stress again that we've only just scratched the surface of what's possible thus far, and there's plenty of room for research, development, and advancement in this area. So Python already has and provides us with a lot of the tools that we need to be able to make a lot of progress with libraries like Pandas and scikit-learn, NetworkX, Seaborn, etc. And so what we need to do from here is combine those tools with the concepts that we've covered here today and start to develop new tools and processes to continue moving forward. And I think that if we can do that, we'll be very pleasantly surprised by both the results that we achieve and the insights that we're able to discover. So if you're interested in learning more about this stuff, my first suggestion would be to keep an eye on the District Data Labs blog. I'm going to be writing a blog post series about this topic. And then we have a couple of open source projects that incorporate some of the topics that we've been covering here. So Cultivar is an exploratory data analysis tool, and Yellowbrick is a Python library for doing visual diagnostics on machine learning. We're going to be sprinting on both of those at the sprints, so please come by and check that out. And if you have any questions or just want to reach out, there's my contact information. Please reach out on Twitter or LinkedIn. All right, thanks a lot, guys.
Thank you, Tony. If you have any questions or want to chat further with Tony, he'll be around here or out in the hallway. You can catch him there. Thank you very much.
PC. I originally got into data science and analytics from a business background. So I studied business in school and started off working as an analyst. And it really wasn't too long before I figured out that if I learned a little bit of programming, I could get my work done a lot faster, and I could do a lot more than the other analysts that I was working with. And so I taught myself how to program, first in VBA, creating these little baby self-contained applications in Excel and Access. And then from there, I taught myself how to program in R. And then about 4 years ago or so, I started programming in Python. And I have to say, I fell in love with it almost immediately. And this was right around the time that pandas was starting to get popular. And so I was like, oh yeah, this is going to make my transition from R to Python so much easier. And so I made that transition, continued analyzing data.
You've heard the fire alarm has been cleared. We are all okay. Nothing is on fire. Everything is fine. Thank you. Thank you. Next piece of administrivia, if you have any device that is capable of making noise, please convince it not to, because if it does, everyone will stare at it and you and mock both of you on Twitter. Our next talk is by Tony Ojeda. He is going to be speaking about human-machine collaboration for improved analytical processes. Please make him feel welcome.
Thank you very much. Hello, everyone. My name is Tony Ojeda, and I'd like to welcome you to my talk on human-machine collaboration for improved analytical processes. So before I dive into the meat of the talk, I'd like to tell you a little bit about me and my background, and then we'll go with Python now. And then I started to get into some of the machine learning stuff, and this was right around the time that scikit-learn started adding a bunch of new features that made doing machine learning a lot easier. And so not only was I learning about all these different cool algorithms that I could use, but I was able to easily implement them, swap one out for the other in my pipelines, and compare all their results. And at that point, I was like, this is awesome, I'm Superman, right? I could do all these things, and I thought it was like super awesome. And so now, it's been a few more years, and the advances in machine learning and automation are starting to come together, and we're starting to see a resurgence of artificial intelligence. So things that were harder to automate previously are starting to become a lot easier now. And in fact, if you read any technology publications in the last few months, chances are you've come across headlines. Go ahead and jump right into it. So I'm a data scientist at Follett. They are a higher education, wholesale, and retail company. And I use Python, analytics, and machine learning to build data-driven processes that help drive that company's business there. I'm also the founder of District Data Labs, which is a data science research institute and open source collaborative based out of Washington, D.C. We have a variety of open source projects that we build with Python, and we use Python extensively in our corporate training and consulting offerings as well. I've co-authored a couple of books. There's Applied Text Analysis with Python, which is an O'Reilly book that's coming out this fall, and then the Practical Data Science Cookbook, which was published by PACT a couple of years ago. And this is my fourth time speaking at a conference. Last year I spoke at Data Day in Seattle and at PyData Carolinas and PyData lines like these, right? So artificial intelligence in the end of humanity, artificial intelligence is going to take your job, right? All very scary kind of dystopian things. And so naturally I started to ask myself, well, could what I do actually be completely automated? And so of course I did some additional research on this to basically see if I could find some information that would tell me and help me figure out how long I had before I was essentially obsolete. But as I was reading through all these papers and articles and blog posts, I started to come to the realization that maybe I was focusing on the wrong question, or if not the wrong question, not the most applicable one to me in the near future. And so instead, I decided that a better question would be, how can we combine human and machine abilities to produce better outcomes than either could on their own, right? How can we